So this will be the third lecture out of chapter 19. So in the second lecture we looked at reactions that make amines, and in this lecture we'll look at the reactions that amines undergo. So one of the most fundamental reactions that amines undergo is, so amines are bases, so if you react them with an acid, then they'll just do an acid-base reaction. So if we take an amine with a carboxylic acid, then it would just take the hydrogen off of the carboxylic acid, and you would end up with this salt. So you can use this to your advantage in lab, for example, because you can change the solubility properties of an amine this way. So if you took aniline, for example, which is not water soluble, and you reacted it with HCl, then the lone pair of nitrogen picks up a hydrogen from HCl to make the ammonium chloride salt, and then now that's water soluble. So how could you utilize that, for example? So let's say you had a mixture of aniline and this ketone. They're both organic soluble. So how can you separate them? So we're going to separate them through a process called extraction. So we would put them into a piece of glassware called a separatory funnel, for example. And if we use an organic solvent like ether, so ether could dissolve aniline and cyclohexanone. And then if we add some 1 molar hydrochloric acid that's dissolved in water, so the ether is going to, the cyclohexanone is going to stay dissolved in the ether layer, which is now going to be the top layer because ether is less dense than water. And since we have HCl present, then the aniline is going to react with that HCl to make the ammonium chloride salt, which is going to be water soluble. So now we have two layers, an ether layer and an aqueous layer. The ketones in the ether layer, the ammonium salt, the aniline is in the water layer. We now have them separated. So what you could do now is drain the bottom layer, the water layer, out the bottom into a beaker, and leave the cyclohexanone in the ether layer in the separatory funnel. So now you have them physically separated from each other. So you can isolate the ether by simply putting it into a flask, cyclohexanone, by putting the ether layer into a flask, evaporate the ether off, and now you have the cyclohexanone pure. And if you wanted to recover your aniline, well, right now it's in the form of a hydrochloride salt, so you would need to neutralize that. So what you could do is add some base, for example, to the aqueous layer and monitor the pH using pH paper or a pH meter. And when the pH was neutral, then now you have aniline. So whatever the base was, if it was not water soluble, then it would precipitate out at this point. If it's a solid. If it's a liquid, then now it's not water soluble, so you would see another liquid layer forming. So if it's a solid, you could just filter it off, or if it's a liquid, you could just pipette it off, since it's now going to be two layers. So basically, point is, since amines are bases, you can manipulate the acid-base property to change solubility so that you can get it to go into different layers to an aqueous layer, whereas an organic molecule that doesn't have acid-base properties would just stay in the organic layer. Okay, so quickly, if we just review the different reactions of amines that you do know. So ketone and a primary amine. It makes an imine. Ketone and the secondary amine makes an enamine. We looked at this in the last chapter, acid chloride and an amine makes an amide, and we'll look at the mechanism for that reaction when we look at the acid chloride chapter 21. Or amines with alkyl halides will do SN2 reactions. You just have to keep in mind it doesn't stop there. You can over-alkylate it, where this reaction could happen 3 more times and go to or 2 more times and make the quaternary amine. Right, so you can make since you started with a primary amine, and then you make a secondary amine, and then you could make the tertiary amine, and then it could react again to make the quaternary amine. Okay, so this is another reaction that amines undergo. It's called Hoffman Elimination, or a process through what's called exhaustive methylation. So if we take this amine with its which is primary, and react it with excess methyl iodide, then the nitrogen is going to keep reacting with methyl iodide until it's quaternary, right? So now nitrogen's got 4 bonds, so it's positively charged, and the counter ion would be I minus, coming from the methyl iodide. Okay, so that would make this. And so now if you take that and react it with silver iodide, then what happens here is that silver will precipitate the iodide out. And in the process, it will also swap out what the conjugate anion is. So, or rather than I minus, or the counter ion, it'll swap out what the counter ion to the N plus is. So initially it was iodide, but now silver iodide is not very soluble in water. So it'll precipitate out. And now you have hydroxide, and hydroxide's a base. And if you heat this, so that's a base with heat, this can do an E2 elimination. And so the significance of this is that this is a bulky leaving group. So we've seen E2 reactions with bulky bases before. If you remember, that does a Hoffman elimination. Well, it's the same principle here. If you have a base with a bulky leaving group, it'll do a Hoffman elimination. So the situation is that the NCH, so the nitrogen with 3 methyl groups is a leaving group. It'll come off as trimethylamine, and it's so big that it makes the base attack the hydrogen takes the hydrogen off from the most accessible carbon, which will be from the CH3 at the end. So hydroxide takes that hydrogen, these electrons become a double bond there, and trimethylamine leaves. So you make that as a major product, and you get as a leaving group trimethylamine. Because the other possible alkene that you could have made would be, you could have lost a hydrogen from this carbon, but because the leaving group is so bulky, that hydrogen is not very accessible because it's on a tertiary position, right? Whereas this hydrogen's on a primary position. That hydrogen's more accessible, so this is the product that you make, which is the least substituted alkene. And if you remember, the least substituted alkene is called the Hoffman product. Where the more substituted alkene is called the ZF product, right? So this elimination leads to the Hoffman product. So if you notice, so it took one sequence to liberate trimethylamine. So this tells you how your amine is substituted, whether it's primary, secondary, or tertiary. If it only took one sequence of those reactions to make trimethylamine, it was a primary amine. Whereas this one is tertiary, and as we'll see, in order to free up trimethylamine, you would have to do this reaction 3 times. Okay, so let's go through this. So nitrogen is going to attack CH3, kick off iodine. Since it's already tertiary to begin with, now it's going to be quaternary. Right, so now that's a quaternary amine. It would initially be I minus, and then you do the second step, and then so that precipitates out, and now you have hydroxide instead. And now you heat this up, so it's going to do an E2 elimination, which means you have 3 potential bonds that you could break. Right? You could break this bond, you could break that bond, or you could break this bond. So let's we'll call this A, and we'll call this B, and we'll call that C. So if you put the double bond at A, so which means the double bond would go here, which means you'd have to lose a hydrogen from here. All right, so this takes the hydrogen from here, those electrons go there, and this bond breaks, and that becomes a lone pair nitrogen. So if you did put the double bond there, that would be a mono substituted, right? If you put the bond at B, then that would mean you would have to take the hydrogen from here, so the bond would go there, and that, if you put the double bond there, it's disubstituted, and so that would be C, sorry. And if you wanted to break bond B, then you have to take the hydrogen, no, not from there. So you can't take it from here because there's no hydrogens here. So you would have to take it from here, and then the double bond would go there. And if you put the double bond there, by breaking bond B, then that would be a tri. Well, this gives you the Hoffman product, so what's going to happen is you're going to take the hydrogen to make the mono-substituted alkene. So this is the one that's going to happen, right? OH is going to take that hydrogen, and you're going to make there's a methyl there, there's a methyl there, and now you've broke that bond from that carbon to nitrogen, so you have a mono substituted alkene, and of course nitrogen has a methyl group attached. Now you repeat the process. So that nitrogen picks up another methyl group, makes it quaternary again. Oh, sorry. Let's see. Let's move this. And let's move this. Let's get rid of this. But that's the product from this reaction. And so now we're going to take that and do the sequence again. Okay, so now this is going to react here and kick that off. No. Right now it's quaternary again. You had I minus, and then that gets precipitated out, so now you have hydroxide. And now we have the choice of putting the double bond here by taking that hydrogen, or we have the choice, this is not drawn right. Or we have the choice of putting the double bond here by taking that hydrogen. And again, putting the double bond at C is less substituted than the B, so this is going to take that hydrogen. Those electrons are going to go here, and we're going to open that. And we're going to break that bond, that becomes a lone pair on nitrogen. So now we have Now we have that. So we went from a monosubstituted double bond, now we have a disubstituted double bond. Trimethylamine has still not been liberated from the molecule, so we'd have to do the sequence again. So another methyl iodide, silver oxide, heat sequence of reactions. Okay, so take a 1-pro nitrogen, repeat this process. That attacks here, kicks the methyl group off. Right now your amine is quaternary again. And now we're going to take the hydrogen from here. Those electrons go there. And now trimethylamine comes off. Right? And you would know when trimethylamine comes off because it would smell at that point, because amines smell pretty bad, especially these low molecular weight amines which have high vapor pressure. So there's a lot of them in the gas phase. Whereas if the starting compound has a very high molecular weight, so that molecule would not have many molecules in the gas phase. Okay, so that's basically an exercise in logic, is trying to take a starting amine like that and be able to work through a sequence of exhaustive methylations to predict what Hoffman product you would form at each step in the reaction. So again, so this used to be used as a way to figure out if you had an amine, is the amine primary, secondary, or tertiary. You would know based on how many sequences you had, how many times you had to repeat the sequence of reactions before you had trimethylamine come off the reaction, right? If it's primary, it only took one sequence before trimethylamine come off the starting material. Or if it's tertiary, you had to repeat this process 3 times before trimethylamine came off. Okay, but it can be used synthetically in order to make a least substituted alkene. So if we contrast this alcohol to this amine, for example, if you did the secondary alcohol with sulfuric acid, if you remember, that will undergo dehydration, or you would make that alkene. But if you did the Hoffman elimination, so if you made the trimethylamine, so if you started with that and did the CH3I and then the silver oxide, and then heated that up, then you would make the Hoffman product, least substituted alkene. Right, where hydroxide would take a hydrogen from here. Those electrons become a double bond, and trimethylamine comes off. Okay, so that's your reactions of amines. So we'll have one more lecture. We'll look at a few more reactions of amines.